Hello, my name is Thomas Steckman, and I'm presenting results on the scalable fabrication of high-mobility, ultra-thin organic field effect transistors using a method known as floating film transfer. This work was conducted at North Carolina State University, where I'm an undergraduate student, under the guidance of Dr. Masur Nahid, Professor Harold Ade, and Professor Abai Gadiza. Floating film transfer, or FTM, uses a spontaneous spreading effect of certain solvents, in our case, p-xylene, over the surface of a liquid substrate, usually deionized water. Because it is a particularly scalable and efficient method, it warrants further study on the effects of polymer morphology and the mechanisms for controlling film formation. Once the film is formed, we are able to stamp it onto the surface of a substrate. In this work, we cast N-type N2200 films and transferred them onto OTS-treated patterned OFET substrates, compatible with both top and bottom gate configurations. The goal of this study, then, was to understand the mechanisms through which we can control the film morphology and thickness, and more importantly, understand the influence of FTM on the electrical performance of ultra-thin film devices down to the monolayer regime. Here, we have two films, a predominantly monolayer and predominantly bilayer film imaged through atomic force microscopy. We're able to control the film properties down to the region of partial layers by controlling droplet size, concentration of N2200, and the surface area of the liquid substrate. Our key result is that FTM monolayer and bilayer films do not suffer the electron mobility performance drop found in prior results for Langmuir-Schaefer and spin-coated methods. We expected an order of magnitude drop in mobility as we approached the monolayer regime, which is a result that has been found experimentally but is not necessarily required by the theory for surface charge density. Comparing spin and FTM devices shows that even in the monolayer regime, FTM devices perform as well or outperform spin-coated devices, which are much thicker, at about 20 nanometers thick. Furthermore, FTM devices perform well regardless of device architecture, which indicates that in thin films, the monolayer morphology is favored for charge transport, and FTM devices maintain similar morphology at the interface even up to 5 molecular layers thick. Thank you.